Now we're going to have a discussion about polyprotic acids. And how they dissociate in a stepwise fashion. We know that polyprotic just means many protons, many hydrogen ions in a formula. Just to remind ourselves of some notes, a monoprotic example might be HCl, a single proton in hydrogen chloride. A diprotic acid, something like carbonic acid, H2CO3. And a triprotic acid, like H3PO4. Mono, di, tri. So when we say polyprotic, we just mean more than one H hydrogen when it comes to an acid. And polyprotic acids always dissociate in a stepwise fashion. So I'm going to write, they always dissociate in stepwise. In other words, we always take off one hydrogen at a time in a dissociation equation. So the first hydrogen comes off much easier than the second. Therefore, the Ka for the first step is much bigger than the Ka for the second step. And if there was a third proton, then the second comes off a bit easier than the third. We denote the stepwise fashion of a polyprotic acid by saying Ka1 for removing that first proton. Ka2 would be the acid dissociation constant for the removal of the second proton. And if there is a third, then Ka3 would be the removal of the third proton. It's always easier to remove the first and the second than the third, and the magnitude of the Ka's becomes successively smaller. So again, the Ka values become successively smaller. Always easier to remove the first than it is to remove the second, and then easier to remove the second than it is to remove the third. So let's look at an example here. Let's say that I have a diprotic acid, and we'll just call it H2X, X signifying whatever the anion is. Let's say it's carbonate. And we're going to remove one, we'll show this, and we'll have our one proton removed plus HX negative. So this is just showing the removal of the first proton, leaving us with HSX negative. And this would have a Ka value of 1. And what we're trying to show is that the removal is easier for this one than the successive. So let's remind ourselves that some conjugate pairs, we know that this would actually be in water, right? So here's our acid, or conjugate acid, and our conjugate base. And this is when we're looking at Bronsted-Lowry pairing, right? So this base, however, then becomes the acid if we want to remove another hydrogen. So then we have our Bronsted-Lowry conjugate acid and a conjugate base. This conjugate base then, to remove that extra proton, becomes our acid over here. And when we go to remove it, we're going to actually have a greater arrow going to the left because it's wanting to stay in its molecular form over here. And we'll break apart the H plus and the X2 minus. And this will give us our Ka2 value. And so the Ka2 is significantly smaller than Ka1. So Ka1 is larger because remember, we just said it's easier to remove the first proton from a polyprotic acid than to remove the second. So those Ka values become successively smaller. So when we are looking at the continuation of our notes, the base in the first step is the acid in the second. As long as the Ka values differ by a factor of 10 to the third or more, so it's possible to obtain a satisfactory estimate of the pH of polyprotic acid solutions by considering Ka1. So this is really important. The pH, we can estimate the pH of the polyprotic acid solutions by just looking at Ka1. And so therefore, we can use this to find the pH of the solution. Let's work through this with an example problem. So we have the solubility of carbon dioxide in pure water, and 1 atmosphere pressure is 0.0037 molarity. Common practice is to assume that all of the dissolved gas is in the form of carbonic acid. So what is the equation for this reaction? Well, we have a combination reaction. We have carbon dioxide in pure water. So let's write this out. CO2 plus H2O react to form carbonic acid, which is H2CO3. All right, so now we're going to show the dissociation of this acid. So we have our H2CO3, and this is our acid. And again, when we're thinking about Bronsted-Lowry acids and bases, we're putting this in water. So our water is acting as our base. And we know 0.0037 molar of this acid. And so we're going to dissociate into our H plus, our conjugate acid. And we know that because it's in water, this is actually our H3O plus concentration. But we know that H3O plus and H plus are used interchangeably. So we have our H plus, and we have, if we took our acid and we just removed 1 proton from that, we're left with HCO3 minus, which is our conjugate base. And I'm going to need to look at our Appendix D here real quick to find Ka1. Looking at our chart here, we found carbonic acid H2CO3 with a Ka1 of 4.3 times 10 to the negative 7th. That is our dissociation Ka value. So we know our initial concentration, and we know that we have a 1-to-1 ratio here. So we can call this X and X. This is for my initial concentration. Now, if we were to write our Ka expression, so we know that Ka is equal to our products, so our H plus times our HCO3 minus over our reactants, H2CO3 concentration, and that's going to be equal to our Ka1 of 4.3 times 10 to the negative 7th. All right, we know that X and X, we can simplify and say X squared on top of here, so we can say that x squared over our H2CO3 concentration, so 0.0037 molar, is equal to our Ka of 4.3 times 10 to the negative 7. So let's simplify this, and we've got 4.3 times 10 to the negative 7 times 0.0037. So, and then that'll be equal to x squared. X squared is equal to 4.3 times 10 to the negative 7 times 0.0037. And then in order to get x by itself, we have to square root it. So let's figure out what x is. So let's do the square root of 4.3 times 10, square root of 4.3 times 10 to the negative 7 times 0.0037. You should get 3.99 times 10 to the negative 5th. So x, which is equal to concentration of H plus, is equal to 3.99 times 10 to the negative 5th molar. Now remember that the pH for polyprotic acids is solved from Ka1 calculations. So we can take this concentration of our H plus and do the negative log of 3.99 times 10 to the negative 5th. And let's see what we get. So let's just do the negative log of our answer to get a pH. So we have a pH of 4.40. All right, good work. So again, to recap what we did, we wrote out carbon dioxide and pure water to give us carbonic acid, H2CO3. All right, we wanted to look at carbonic acid dissociation. So we have our acid in water, which is the base, and we found our Bronsted-Lowry conjugate acid, conjugate base. We looked up carbonic acid, Ka1 constant. We knew the concentration that we started with this acid, and we knew that because of 1-to-1 ratio and that we started, we needed to find these x's. So x times x is x squared over our 0.0037. So we had x squared over 0.0037 equals 4.3 times 10 to the negative 7th. Again, this was from our appendix D. So solving for x means solving for our H plus. H plus also, so even though it's a polyprotic acid, the pH for polyprotic acids is solved from Ka1 calculations. So we were able to just take the negative log of our H plus to get a pH of 4.4. But now there's a second part to the problem. What is the CO3 2 minus concentration? So this is wanting the carbonate. And now remember, in our first dissociation, we took our H2CO3, we took off 1 proton, and that left us with the conjugate base of HCO3 minus. But we want just carbonate. So we need to go one step further, and we need to then take this base and make it the acid, similar to what we did here. We took our H2CO3 made it the acid, took off 1 proton. Now we need to take this HCO3 minus and make it our starting point, make it the acid. So we've got our HCO3 minus, and in this case, our equilibrium is going to look more like this. So to pull off that proton will give us H plus and CO3 2 minus. And this, since we're doing it the second time and pulling off that second proton, is called our Ka2. And if we look back here in our original problem, it tells us that Ka2 is 5.6 times 10 to the negative 11th. So now let's look at what we know. We solved from our last problem what H plus was, right? We solved for H plus was equal to 3.99 times 10 to the negative 5th. And that was our X, right? We solved for X. X was our H plus, and it also was our HCO3 minus. So in this problem, we know our H and we know our HCO3 minus. So let's plug in that value that we found for H plus being 3.99 times 10 to the negative 5th. And we also know that our HCO3 was 3.99 times 10 to the negative 5th molar. So now we just have one unknown. We'll call this our X, our CO3, a concentration of carbonate. So let's set up our Ka equilibrium. So this is for Ka2. We're going to do products over reactants. So the concentration of H plus times carbonate all over bicarbonate HCO3 minus. And so let's plug in what we know. 5.6 times 10 to the negative 11th is equal to 3.99 times 10 to the negative 5th, right, over, times X, because we don't know our concentration of CO3 2 minus, all over 3.99 times 10 to the negative 5th, the concentration of HCO3. So if we look at the math here, we can see that 3.99 times 10 to the negative 5th and 3.99 times 10 to the negative 5th cancel out. So I'm left with X is equal to, which is our concentration of our CO3 2 minus, is equal to 5.6 times 10 to the negative 11th molarity. So the math ends up just canceling these out. So X is equal to that Ka2 in this case. So if we were to go back to review, this is for a diprotic acid. To get my diprotic acid, I did CO2 plus H2O, H2CO3. And then we watched it dissociate into H2CO3 to H plus and HCO3. That conjugate base then became my acid when I wanted to dissociate it a second time. So then I was left with H plus and CO3 2 minus. Notice that I took off that hydrogen to get CO3 2 minus. So that was my conjugate base for my second time. Then we notice for Ka1 that the pH for our polyprotic acids was solved from Ka1 calculations. So this number that I found for H also for Ka2 was the same one. If there was a Ka3, my H plus would be the same for all subsequent polyprotic calculations. So let's look at an example where I have a triprotic acid. So for example, if I had, one of the most common triprotic is H3PO4, which is phosphoric acid. So if we were to look at this dissociation, Again, remember the first one's the easiest to pull off. I would have H plus H2PO4 minus, right? So I went from H3 to H2, and that's called our Ka1. All right, so if I wanted to pull off another hydrogen, another proton, I would start with my H2PO4 minus, and my equilibrium would look a little bit more like this. And I would pull off my H plus again, and then I would only have one HPO4. And instead of just minus, I took off an extra one, it'd be -2, and this would be my Ka2. And if you go one step further, this conjugate base can then become my acid. And I could start with HPO4, 2, and then a little arrow and a much larger arrow going left. And I would have my H plus and a PO4 -3, or 3 minus. And that would be my Ka3. And through doing my very first Ka concentrations where I find my H plus and I can find my pH, that value is the same for all of these calculations. The one that I found in Ka1. And then again, I would find these two because they're both X. This would then carry down to here. And same with after I find my X here, that would then carry down to here.